Okay, so what we're going to do today is we're going to do generating functions. So we saw generating functions earlier in the year when we were doing the mathematical modeling lectures. We saw it with the Fibonaccis. To me, generating functions are almost magical. You take a sequence you don't understand, you package it together, and somehow you can then extract information about that initial sequence. And the reason that you're able to do this is in many cases you have a nice closed form expression for generating functions. And if you have a closed form expression, you can extract properties from it. So again, this is the difference between probability and statistics. We are searching for closed form expressions where we can have these exact answers, where we can infer things from them. We're not doing simulations. Simulations are extremely important. And I will be giving you a problem on the next homework assignment where you can either do it theoretically or you can do it numerically. It's going to be a very tough theoretical calculation. Being able to simulate the answer, being able to write code is going to be useful. But if you ever have a situation where you have an exact formula, the hope is you can extract something useful from it. All right, so what we're going to do today is look at generating functions. There's a lot of different ways of defining the generating function. Depending on which definition we use, we put a different word in front of it. Maybe it's the generating function, maybe it's the probability generating function, maybe it's the moment generating function. These slight tweaks are because they lead to different algebra. And depending on what problem you're looking at, different ones will be more useful. If I want to understand moments, moment generating function, well, the name is probably giving away why we might want to look at it. Right? It's designed to be very tractable for stuff like that. So the idea is the following. We'll first do the discrete case. So we have some sequence n goes from 0 to infinity. Maybe it goes from 1 to infinity, maybe it goes from negative infinity to infinity. I have some sequence that's at most countable. Okay? And I want to build a function from it. So I'll call it GA of S will be a sum n goes from 0 to infinity of an s to the n. All right? So this is a really nice function if the a's are chosen appropriately. And the idea is if we choose these a's appropriately, we might be able to evaluate the sum in closed form and then know something about GA of S. And if we know something about GA of S, then maybe we can do things about the individual a's. Okay? So we saw earlier the Fibonacci case. So we'll call it GF of S was the sum n goes from 0 to infinity of Fn s to the n. If memory served, it was 1 minus s squared. And what we did is we used partial fractions. We wrote this as a over alpha minus s plus b over beta minus s. And then we used the geometric series formulas to expand both of these. So one of the things you might do is you might actually pull out this and write it as 1 minus I'm trying to think how I want to do it. I'll do it s over alpha, and then 1 minus s over beta. And now if s is sufficiently small, I can expand these using the geometric series formula. And this is what led to Benet's formula. So this is a review. We did this earlier in the semester. And if I'm pulling things out like this, if I'm pulling out an alpha, these numbers would change slightly. Or you could absorb those into the constants a and b. So this is using the partial fractions. And now we would be able to get a nice formula for the fn's. So to me, this is miraculous. We start off with a relationship for the fn's. Fn plus 1 is Fn plus Fn minus 1. F0 is 0, F1 is 1. We build up this function. And amazingly, this function has a closed form expression. We will see other sequences where initially we do not have a nice closed form expression for them, but because we can work with the generating function, we can then pull off these coefficients. There's lots of ways to pull them out. Over here, we actually use partial fractions, we expand this out. You could also take derivatives. If I want to figure out the nth coefficient, take n derivatives and set s equal to, so I want the nth term, take n derivatives, and what should I set s to? What's a good value for s? 0. So if I just take s equals 0 right now, the only thing that survives is the f0 term. If I take one derivative, I'll get f1, and then I'll have plus 2 f2s plus 3 f3s squared plus 4 f4 s cubed. And so if I set s equal to 0, I'll be left with just the f1 term. There'll be annoying factorials coming in from taking the derivatives. So if I want to pull off these coefficients, I'm going to have to deal with those factorials. It's not a huge deal because we know exactly what it is. If you know how things are screwed up, and it's not screwed up in too bad of a way, you can clean it up. If there's mixing going on, that's a different story. All right, so this is the generating function for the Fibonacci's. So what we can do now is we can look at lots of different choices. So choices for the A's. So probably the easiest is A0 equals 1, AN equals 0 otherwise. You can't get much easier than this. There's only one term. So in this case, we get GA of S is just 1. Right, not a big deal. This converges for all values of S. So converges for all S. Another, maybe we take AN is R to the N. And then that will give us GA of S will be the sum, n goes from 0 to infinity, of R to the N, S to the N. Well, how should I view R to the N, S to the N? How should I look at this? As RS to the N. So it'll be the sum, n goes from 0 to infinity, of RS to the N. So if we know the geometric series formula, this is true. Is this true for all S? No. What do I need for this to be true? RS less than 1. Now, we're given R. I apologize as a Bostonian. This is one of the only things I will apologize for from being from Boston. We're given R. R is fixed for us. It's S that's free. So I don't want the condition phrased as RS. I want the condition phrased in terms of S. So how would you phrase the condition in terms of S? So it converges if what?
Less than 1 over R.
Good. If the absolute value of S is less than 1 over R. So again, R is fixed, R is given. And so given an R, this series will make sense as long as the absolute value of S is at most 1 over R. So unfortunately, the series may not converge for all values of S. But this at least converges in a neighborhood of S equals 0. Is it hard to get convergence when S equals 0? No, when S equals 0, the only term that survives is the A0 term. Okay, so I could give you is maybe AN equals n factorial, and that will give us, GA of S will be a sum, n goes from 0 to infinity of, let's do 1 over n factorial, of S to the N over n factorial, which is e to the S. This converges for all S. And let's do one last one. The one I was so eager to I got to a moment ago, AN equals n factorial. This leads to GA of S equals the sum, n goes from 0 to infinity, of n factorial S to the N. Any thoughts about what values of S will lead to this sum converging? When does this converge? Converges for, what do you think? S equals 0. Anything else? It diverges for all other S. So imagine S is 1 over 1,000. Eventually, I get to the term that's 1,000. I get to n is 1,000. Then the next will give me 1,001, which will be larger than that factor. So if you're thinking about what's going on, I can look at n factorial S to the N as say n minus 1 dot 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 to 1001 times s times s to the 1000 over 1000 factorial. And so what I can do is I can say, look, I've got a couple of terms in the beginning. Let's say s is 1 over 1000. Well, if s is 1000. So s is, no, let's do 1 over 1000. So s is really small. Because s is really small, this is going to be very nice when n is small. S is small, high powers of s are going to be very negligible. The danger is, even though this is getting small, n factorial is getting large very quickly. And maybe the n factorial will grow faster than the s sub n will shrink. Let's quickly see why that might be true. So if s is like 1 over 1000, once n gets larger than 1000, to get to the next term, I decrease by a factor of 1000 by adding one more s, but I increase by more than a factor of 1000 going from n to n plus 1. So from that point onward, I'm increasing faster than I'm decreasing, so all the terms are going to be increasing from that point onward. So from the 1001st term onward, the sequence is increasing. If the sequence is increasing, the sum is going to diverge. And so what I'm doing here is I'm just pulling out the first 1000 terms. It's something, and then this thing over here is going to be greater than 1. So again, you can have the unfortunate situation where you will have a series that will only converge at s equals 0. Because of that, some generating functions are not that useful to work with. Can you think of any probability distribution that might have a bad generating function attached to it? Cauchy. Why might the Cauchy have problems? Yeah, we can argue whether or not the Cauchy has a mean. It definitely does not have a finite variance. So one of the whole problems is, if you want to work with generating functions, it's nice if the generating function exists. We will see a way to look at not the standard generating functions, but a tweak. The probabilists call it the characteristic function. The analysts call it the Fourier transform. And what we'll do is, we'll talk a little bit about this in this class. It involves using the square root of -1. It uses complex analysis, but it always exists. And it always converges. And there's a huge benefit for something like that. OK, so what we want to do now is we want to talk a little bit about why we might care about generating functions. How many of you have taken linear algebra? How many of you remember how to multiply matrices? This should be almost the same question. How many of you know why we multiply matrices the way we do? So why do we multiply matrices the way we multiply them? I mean, if you've seen the definition of matrix multiplication, this should look very unnatural. You know, having all these dot products and those are coming as the entries. But like good little students, you've been taught that this is what you're supposed to do, so you've learned it, you multiply matrices like this. Great. Why? Why do we multiply matrices like this?
Because we felt like it.
Well, no, actually, the people before you felt like it, and they're insisting that you follow them. This is why we have the QWERTY keyboard. This is why we're still on the English system. Yes?
My guess would be because each column entry is a vector, so it's a vector multiplication, as opposed to just going systematically.
So let's imagine we have a matrix A acting on a vector B, and then we want B to act on this. Well, if we call this thing W, we know how to have a matrix act on a vector. I want to define matrix multiplication in such a way that BA is some operator C. And I want, BA acting on V to be the same as B acting on A acting on V. And when you unwind this, this forces you to the definition of matrix multiplication that we do. And the reason is a matrix is a representation of a transformation. So A and B represent transformations in a basis. Depending on what basis you choose, the matrix representation of the transformation will look differently. Again, I think I apologized earlier for being from Boston. I will say something nice about New York. Which part of New York City, as a mathematician, do I like? I'm sorry? No, it doesn't depend. Oh, I'm sorry? Manhattan. I have to say hats off to Manhattan. It is a beautiful grid system. Okay, it's very easy to talk about the coordinates as to where you are and how you're moving. In Boston, you will have streets like Comm Ave and Beacon that are crossing each other. So depending on where you are in Boston, they'll flip. You'll have horrible one-way situations in Boston. It's a nightmare to get around. Manhattan, it's a beautiful grid. There's a very natural coordinate system. The whole point of linear algebra is, depending on what problem you're looking at, you choose an appropriate basis. If you want to study an ellipse aligned with the coordinate axes, this isn't so bad. It's x over a squared plus y over b squared equals 1. If instead I give you an ellipse like this, the trick is you first rotate your coordinate axes, you study it in this basis, where it's now aligned with the axes, and then you rotate back. And you can unify all of this in that way. So it's always good to have a sense of why we're doing what we're doing. Where does this all come from? The reason we do matrix multiplication the way we do is matrices are transformations written down in a basis. Depending on what problem you're working on, different bases are more convenient. Linear algebra is all about converting to the most convenient system possible for calculation. We will see a lot of that when we do generating functions. So the idea is we want to look at the generating function that will be the easiest. So let's say I give you two polynomials. F of x equals the sum. Let's say n goes from 0 to, let's go to infinity. An x to the n. G of x will be the sum. M goes from 0 to infinity of bm x to the m. We'll assume these polynomials converge. If you are worried about convergence, what should you do? I'm sorry? Take real analysis. Okay, so if you're worried about convergence, take real analysis. If you don't want to do that, then replace infinity with some large finite number, and then everything will converge because it's finite. We have two polynomials. There are two natural things you can do to them. What's one natural thing we can do to the two polynomials? We could add. What else could we do? Actually, I guess there's three natural things we could do. We could add them. What else could we do? Subtracting is the same as adding backwards. We could multiply. The third one is we could actually have f of g of x. We could do almost like a chain rule situation. But let's do multiplication. Let's do f of x times g of x. Do we have to consider g of x times f of x? No, multiplication is commutative. That's going to be extremely important later. We've already seen arguments like this. Because of commutativity of addition, things become nice. So we have a0 plus a1x plus a2x squared times b0 plus b1x plus b2x squared. And now we multiply them together. So I'm going to just multiply and collect terms. So what's the constant term going to be? Only way I can do it is a0 times b0. Now let's look at the linear term, the term that has just an x. It's going to be a0 times b1x, a1x times b0. So the next term is a0 b1 plus a1 b0 times x. How can I get an x squared term? I can have the x squared times the b0. I can have x times x, or I can have a0 times b2x squared. So the x squared term will be I'll do it this way. It will be a0 b2 plus a1 b1 plus a2 b0 x squared. If I want to do the cube term, it would be a0 b3 plus a1 b2 plus a2 b1 plus a3 b0 x cubed. Okay. Does this look familiar at all? What does this look like?
Kind of like a dot product.
I'm sorry?
A dot product.
It looks a little bit like a dot product, but in a standard dot product, we have the same components hitting each other. So if I were to dot these functions together, maybe I would have a0, b0 plus a1, b1x plus a2, b2 x squared plus a3, b3 x cubed. That would be a very nice definition of multiplication. If you had your wish list for how to multiply polynomials, term by term multiplication would be really nice. By now, your hopes should be shattered. All your wishes, you should have learned, not going to happen. What does this look like? We've seen this before. So I'll write the general term as a sum. L goes from 0 to k, a sub L, b sub k minus L, x to the k, and then we'll have a sum k goes from 0 to infinity. And that'll be f of x, g of x. What does this look like? It looks like a convolution. Why does this look like a convolution? Well, the sum of the indices is always k. So if you think of this, a nice way of thinking of it is, what if AL is the probability that my first random variable is L, bk minus L is the probability that my second random variable is k minus L, and the random variables are independent. This sum would basically just be the probability that the sum of the two random variables equals k. And now you can begin to see why we're going to spend so much time on generating functions. Okay, so when we formally put in what's going on here, this suggests that convolutions and generating functions are related. And so formally, see, can we be able to see? Okay, so given a sequence A and B, define the convolution C equals A star B by CK equals the sum, L goes from 0 to K of A, L, B, K minus L. And then we have the following theorem. GC of S equals GA of S, GB of S, when the series converge. As real analysis is not a prereq, I'm not going to go into too much detail about if G of A converges for S sufficiently small and G of B converges for S sufficiently small, then their product converges for S sufficiently small. If you want, that's a really nice exercise to try to do and figure out if they both converge, what can you say about their product converging? I'm going to just assume that for now. Why is this true? It's essentially by definition. GA of S, well, the only difference between that and f of x is I'm using the letter S rather than the letter x. And GB of S, the only difference is I'm using the letter S rather than the letter x. And if I multiply them together, by definition, that's how I'm choosing C. So the proof is basically by definition. These are either the easiest or the hardest proofs to do, because you feel like there's something you're supposed to be doing. What you're supposed to be doing is noting that we've defined it in such a way that this is going to hold. So just from polynomial multiplication, we now have this wonderful property that if you take the convolution of two sequences, the generating function of the convolution is the product of the generating functions. So, generating function of convolution is the product of the generating functions. This might remind you of all the different log rules we have. The log of a product is the sum of the logs. The log of a quotient is the difference of the logs. Having these phrases is extremely useful. The generating function of a convolution is the product of the generating functions. This is, again, a huge warning that this matters in probability. One of the biggest things we're going to try to study is the central limit theorem. We're going to try to understand sums of independent, identically distributed random variables. Well, what this is telling us is the convolutions will be giving us the probabilities. All right, so let's do an example. I'll do this example two ways. We might have seen this example earlier in the semester. I don't think we actually did this one, but this was in the book earlier, and you can do it by story. So the question is, what is the sum k goes from 0 to n of n choose k squared? And this is the same as the sum k goes from 0 to n of n choose k, n choose n minus k. One of the hardest parts of combinatorics is to tell a good story. Can anybody give me a story as to what this represents? So we'll do the story proof. It's story time. So I don't have any warm milk, but it's dangerous to do that, I think, in a class.
So if you have n objects and you choose k of them, that's the same as having n objects and choosing not k of them?
Okay, that explains why this is the same as the other factor here. But what does this product represent? Yes?
Flipping n coins and getting like k tails. Like in a particular order.
One way of looking at it is I have n coins and I'm choosing k of them to be tails. It's not quite what I want here. Let's see, was it Skidmore we played yesterday in baseball?
Yeah.
Okay, so we have n people from the Williams baseball team and n from the Skidmore team. I was able to go to some of the game yesterday before I had to go to my game. All right? How would you interpret n choose k? So I've got n people from Williams. How would you interpret n choose k? I'm choosing k people from Williams. How would you interpret n choose n minus k? I'm choosing n minus k people from Skidmore. How many people have I chosen overall? N. So as I range over k, this counts the number of ways to choose n people from n Williams adults, and n Skidmore. Because I have to have some number of people from Williams. It's 0, it's 1, it's 2, it's 3, all the way up to n. So this is the number of ways to choose n people from n Williams students and n Skidmore students. Can someone give me another way to count how many ways there are to choose n people from n Williams and n Skidmore people? Yeah, it's 2n choose n. Have 2n people choose n. So this is proof by story. So it's much better to write it as n choose k times n choose n minus k. But if you write it like this, if you interpret this correctly, the proof is one line. Proofs by story are hard. It all comes down to, can you look at something two different ways and notice what's going on? One of the things that's nice about generating functions is they can often convert a lot of these arguments to something that's very formal. Now, I talked a little bit about this, I believe, at the end of class yesterday. How many of you enjoy the quadratic formula? Okay. How many of you are willing to use the quadratic formula if necessary to find roots? Is this an onerous task to ask you to use the quadratic formula? No. You can do it. It's mechanical. It will grind out the answer. We talked about how it's often easier to just look and see the factorization of the polynomial. Frequently these polynomials factor easily because we want the answers to be nice. We want the algebra to be simple. So the homework problems are deliberately designed in that way. All right. So let's look at the following. Let's let GA of S be the sum. M goes from 0 to n of n choose m s to the m. Okay? We're going to look at this generating function. This is going to be related to that one here. I'm going to go through this very slowly because I really want to highlight the algebra. I claim I shouldn't really view this as just s times to the m. I should really view it as s to the m times 1 to the m minus m. And again, I can multiply by 1 at will. I'm not changing anything. But when I write it like this, hopefully it highlights what's going on and how you should look at this. This is the binomial theorem. And this should just be equal to 1 plus s to the nth power. Okay? So we have a nice formula for this sum. We can pull off coefficients easily. If I want the third coefficient, it's n choose 3. If I want the fifth, it's n choose 5. Okay, question? Okay, so now let's look at C equals A star A, the convolution of A with itself. So we know GC of S is going to be GA of S times GA of S. Well, what's GA of S? It's 1 plus S to the n, 1 plus S to the n. So what is 1 plus S to the n times 1 plus S to the n? 1 plus S to the 2n. So we can actually pull off the coefficients very easily. So the sum, I'm running out of letters in the alphabet, M, N, we'll do maybe R goes from 0 to 2n of 2n choose, of CR S to the R is going to just be the sum R goes from 0 to 2n of 2n choose R S to the R. You know, the coefficients here have to just be 2n choose R. Okay, why is this useful? Well, we know that C is A star A. How do we do a convolution? We know C is A star A, so Cn is going to be the sum, L goes from 0 to n, of AL, AN minus L. That's the definition of the convolution. And here, AK is n choose k. So what do we get? We get Cn is the sum, L goes from 0 to n, of n choose k, n choose, I'm doing L, sorry, n choose L, n choose n minus L, and from here, we know that's going to just be 2n choose n. And there's our formula. So without having to come up with the story, without having to come up with an interpretation of what's going on, we can actually see why this identity is true. We could do an entire course on using generating functions, proving identities, finding formulas for sequences and series. We're not going to do that. I'm resisting the temptation. But I want you to be aware that this is out there. I want you to be aware that this stuff can be done. I want you to see the power of the generating series. I really didn't have to do much thinking here. And the reason is because of how the generating function is defined. The hard part is I had to realize I should look at A convolved with A. All right, but once we start looking at that, a lot of things follow nicely. Okay, any questions about this example? Yes?
I have a question of how, like, the beginning of this proof, the story proof changes when there's a certain probability assigned to, like, the lose players, get more players.
Then it's very different.
Yeah, because it's just assuming.
Right, this is assuming that all groups are equally likely.
Yeah.
And if all groups were not equally likely, then this argument would not work and you'd have to have weighted sums. And so there would be a formula that would be true, but there would now be weights. If you want, you can think back to the example we did with Abba, where every person is equally likely to be chosen, but not all groups of people are equally likely to be formed, because with 2 divorces among 2 couples, these were not happy divorces. Okay. Any other questions on this? All right. So if you've started the take-home exam, you'll have seen one of the questions on, musical groups either I or my parents or my kids have listened to. All right, I think next is wish list. Yes, okay. So wish list theorem. So here's something that's trivial. If the sequence A equals B, then GA of S equals GB of S. This is extremely trivial. What's GA of S? Well, it's the sum of A n S to the n. What's GB of S? It's the sum of B n S to the n. If the sequence A equals the sequence B, then the sums are the same. So this is trivial. The wish is that the other direction is true. And that's actually a theorem for discrete random variables, for the situations we'll be looking at. So sometimes dreams do come true. Yes. So we have the following theorem. If GA of S equals GB of S, and both converge for the absolute value of S less than delta, delta is some number greater than 0, then AN equals BN for all n. So the other way of looking at it is, if these 2 series are the same, they've got to be the same term by term, as long as they converge. Again, if you want to prove this really rigorously, you would take real analysis. All right. Imagine the sequences are the same in the beginning, and then they have a first term where they differ. I could subtract off the parts where they're the same, right? So I might as well assume that they differ in the very first term. Right? Do you agree that if they have the first 1,000 terms the same, just subtract the first 1,000 terms? Yes? So we might as well assume that they are the same, that they start differing immediately. I can divide by powers of S, so I can assume that they differ in the constant term. So if not, maybe A0 does not equal B0. And then we would have A0 plus S times blah equals B0 plus S times blah. If you choose S really, really small, these 2 things are going to be very close to what number? For small s, what will these things be close to? They're being multiplied by s. If s is really small, this is close to, and this is close to. If a0 and b0 are not the same, there's some finite difference between them. There's some finite distance between them. So I just choose s so damn small that these things are so close to 0 that even if they went in the right directions together, they wouldn't be enough to balance things out. So imagine this is 1, this is 2. I choose it so that these quantities are at most a third. There's no way to then move them and get them together. So then that contradicts the fact that this was the first place where they differed. And therefore we're done. So this is close to a proof. Okay? Again, you need to be a little bit rigorous. You need to talk about what does it mean for a series to converge. I hope that this is enough to give you a sense. If you want to, I'm happy to chat more about putting in the details. The other thing you could do, what value of s should you evaluate these at? 0. So you evaluate them at s equals 0, and then you see that a0 equals b0. All right, well, we can then subtract a0 and b0 from both sides. We could divide by s and evaluate at 0 again. And you could keep doing that. Or you could keep taking derivatives. And now this is assuming if I'm differentiating, I can interchange a sum and a derivative. So you've got to be a little bit careful with games like that. If a series converges absolutely, you can justify all of this. Again, this is why we have classes like real analysis. But this tells you that generating functions are very nice for sequences like this. If two generating functions are equal, then the corresponding terms are the same. For discrete random variables, this is going to be wonderful. Because what we're going to look at oftentimes is probability distributions that come from quantities that only assume non-negative integer values. 0, 1, 2, 3, 4, 5. So can someone give me a reason why I am obsessed with things that take on non-negative integer values?
Because you can apply the gamma function to them.
I could, but I can apply the gamma function to non-integral values. Why do you think we care so much about things that take on non-negative integer values, that are 0, 1, 2, 3, 4? They're easier to conceptualize, but it's more than just that they're easier to conceptualize. So when I left the Williams baseball game yesterday, we were up 7-2. The final score was, I think, 15 pi, right? Oh, no, it wasn't 15 pi, right? You never...
They just happen in real life.
In real life, all the time, you have things that take on integer values, right? So it's wonderful that integer value things are nice and easy to analyze, but they're also practical. If you want to model things in the real world, how many runs does a team score? You don't score half a run. If you want to count how many failures do we have, we often use the Poisson process to model failures or accidents in an intersection. Now, if you want to talk about how many expected failures do you have, how many expected runs do you have, the expectation might not be an integer, right? If I roll a fair die, what's my expected value for the roll? 3.5. Okay, if you can roll a 3.5, I will give you an A in this class on one die. A standard die. Okay, not going to happen. This new die, wow, every side is a 3.5. Okay, you're not going to see a 3.5 when you roll one die. You're going to get data that is discrete and non-negative integers. That's why we care so much about these quantities. So we will call this the probability generating function. So g x of s is going to be the expected value of s to the x. This is going to be a sum, and it goes from 0 to infinity of the probability that x equals n times s to the n, with x a random variable taking non-negative integer values. So a lot of distributions will be useful here. Rolling a die, flipping a coin, binomial distributions, Bernoulli distributions, how long you have to wait until the first failure, negative binomials. A lot of these processes will be in a situation like this. Okay? And if you think about the definition, what is the definition of the expected value of s to the x? So let me say, writing. Okay, yes. So if I just asked you for the expected value of x, that would be n times the probability that I take on the value of n. If I wanted the expected value of x squared, it would be n squared times the probability I equal n. If I wanted the third moment, x cubed, it would be n cubed times the probability I take on the value n. I'm taking the expected value of s to the n. Of s to the x. So now instead of having x squared, x cubed, I have s to the x. So this is a little bit different than before. Why am I doing it? This is extremely useful. So we can immediately get some theorems from this. So theorem, let's say x1, x2 independent, generating functions converge for the absolute value of s less than delta delta is always greater than 0. What can you tell me about the generating function of the sum? And we'll assume independent non-negative integer. What can you tell me about the generating function of the sum? Sum of the generating functions, g x1 of s, g x2 of s. No. Only semi-accidentally that this side of the board had not been erased. Right? That's the result we need. If we have a sequence defined by convolution, then the generating function of the convolution is the product of the generating functions. If I have two independent random variables and they take on integer values, it's beautiful. It's just the convolution. Okay? So I will let you ponder tonight, in your copious free time when you're not doing the exam, if this would still be true if they were not probability distributions, taking on non-negative integer values. What if they took on real values? Would it still be true? Say a countable sequence of real values. Square root of 2, square root of 3, square root of 4, square root of 5. Would it still work then? Or maybe something more interesting, square root of 2, pi, e, square root of 5, 1,000, something like that. Would that still be true? Are we fundamentally using the fact that these are non-negative integers, or is that just a nice? All right, what do you think the next theorem should be? We have the sum of two independent random variables. I'm sorry? Not product. That's one way to generalize. Instead of doing a sum, you could do a product, and there will be a similar formula. You would have to define convolution a little bit differently. But what's another thing we could do rather than the summing of two independents? More than two. More generally, so to be safe, we should only do a finite number. It'll be the product, k goes from 1 to n, of g x k of s. The proof is by grouping. So if we look at g x1 plus x2 plus xn of s, what we do is we group the last, that's terrible because it intersected the n. We group the last n minus 1 together. And if we group them together, then using the result, this is now just g x1 of s times g of x2 plus xn of s. So this is by grouping. So we've seen grouping many times this semester. Grouping is an extremely powerful technique. We treat the sum of x2 through xn as just one big random variable. And so now we have x1 plus big thing. And so by this result over here, it's now going to be the product. And then we can just keep lather, rinse, repeat. We can do it again. We can say by induction, and we just continue. OK. Any questions on the stuff so far? We have half a minute left. And so it is not worth starting a new unit with half a minute left. So I will stop here. On Friday's class, we will do sums of Poisson. And we'll see now, using this uniqueness result, that if you sum two Poisson random variables, because the sum of Poisson has the same generating function as a Poisson, it's got to be a Poisson. It's not going to be this nice when we get to sums of continuous. So enjoy it while you can. It will not last.